Hi, I will continue. We'll study optimal allocation. So there are two different problems associated with the sample allocation and the sample size determination. Sample allocation is about determining NH, the sample size for stratum H, for a given sample size N. Sample size, sample size determination is about determining the total sample size N. Okay, we'll focus on the total estimation or mean estimation. If the problem is about comparing the difference in the means across different strata, the optimal allocation approach in our class does not apply, and it is beyond the scope of our class. To discuss the optimal allocation, we'll study two different scenarios. The first scenario is when the total budget is given. Okay, total budget is given. The other scenario is when the margin of error is given. In the first scenario, the sample size for each stratum will be directly computed from the total budget constraint. In the second scenario, the sample size determinations will be made in two steps. Step 1, determine the total sample size N, and then step 2, find the optimal sample allocation. Now, let's first consider scenario 1. The problem is to find the sample allocation that minimizes the variance of t hat. So minimize the variance of this guy, t hat str, the unbiased estimator of the total population total on the stratified random sampling. Given for the subject to the constraint that the total cost is less than the given budget. It can be formulated as a purely mathematical problem, and in mathematics, it is called the constraint optimization problem. If the total budget is given, then we need to construct a cost function on the stratified sampling. There are three factors in the cost function. The first one, C0, is the initial cost that such as creating survey questions or other administrative cost. The second one is the direct cost associated with the observation, that obtaining the sample answers. So it is the direct cost and can be different from stratum to stratum. For example, the survey cost in Iowa may be different from the survey cost in New York City. So we will use a CH, subscript H, to denote the cost for surveying one unit in stratum H. The third factor is the sample size. The more we sample, the higher the cost will be. Thus, it is reasonable to assume that the total cost is a linear function of NH and CH, something like this. And C0 is the initial, and then we have per stratum cost, but we have NH, that is the total. So NH times CH will be the total cost in stratum H, and then since we have a capital H strata, we should add up. Now, the optimal allocation, which was first found by Neumann in 1934, can be formulated as minimizing the variance, total variance, subject to the constraint that the total cost is equal to the budget. So in the variance term, if you look at this, the second term does not depend on the sample size, right? It's a free of small NHs. So only the first term matters. So it's just minimizing this first term subject to constraint, and the solution is this guy. Is this form, which is a function of the three factors: capital NH, capital SH and CH. So based using these three factors, we can find the optimal allocation. So we can prove the result using the Cauchy-Schwarz inequality in mathematics, but I will skip the proof. If the total sample size is given, then we can explicitly find the optimal allocation as this. Basically, because this is proportional, right? So since the NH, the optimal NH will be proportional to this factor in the right side, so the proportionality constant is K. So we can write it as NH equal to capital NH is capital SH divided by CH times K, right? And then use this constraint, sample size constraint, to obtain K, and the solution can be easily obtained because it's a linear equation for simple equation for K. So that is the solution. And this solution basically says that if the population size is large, then we should increase the sample size. If the population variance for that straight term is large, then we should increase too. If CH is large, that means we have a cost is high, then we should reduce the sample size. So it kind of makes sense. If CH are unknown, or then we may assume that they are all equal, and so that the optimal allocation reduces to this one. Furthermore, if SH are all unknown, then also we may assume that they are all equal, so the optimal allocation becomes, so if they are all equal, then S will cancel out, right? So then it becomes a proportional allocation. So therefore, we may say that if the costs are all equal and the straight term variance are all equal, then the proportional allocation is actually the best way for sample allocation in stratified sampling. Now, if the total cost is given, then the K in the form of the optimal allocation, so NH equal to SH. So you should first write K and determine K using this constraint. So we plug in here and solve the equation for K. Then the solution is this guy. So this is a formula for optimal allocation when the total cost is given. Now, recall that the variance formula on the stratified sampling. Okay, so the variance on the stratified sampling. Okay, NH SH is square divided by NH minus NH SH square, right? So this is the variance formula on the stratified random sampling. And so this is the allocation, optimal allocation. So basically we can plug in. Okay, so maybe I will use different color. So we can use this one to here. Okay, then what will happen? Then okay, so let me write it again. sh square, and then this guy is, we can write it nh sh. Okay, so if you plug in, then the variance nh square sh square divided by nh sh, and then inverse, right? So minus so actually you can see that this guy is cancelled. So you end up getting h equal to nh sh square 1 over n minus and then you may use nh equal to wh, capital WH and n. Then you can use consistency. Okay, so then n square h equal to 1 to h wh sh square over n minus okay. So this is the another way formula, right? So this is this result. Okay. By the way, this is the optimal. If you use proportional, then you remember we were able to write it like SW square, right? And this SW square is a within. So basically this one is, if you remember, so where did we have that? Here, okay, here. So that's basically this one. So we I should have a page numbers. WHSH square. Okay. So basically, so that means n square divided by n summation. I don't know whether we can see it clearly in the YouTube, but should make it more clear. Okay. So if you compare these two, so use different color, maybe. The second term are the equal, the same. Only the only difference is this term and this term, right? Okay. So basically this excuse me. So you see that the second term are the same. Only the only difference is the first term. And you might wonder which one is bigger. Well, thing is, optimal estimator by definition supposed to be best, supposed to be smallest, achieve the smallest variance. So you may think that you may conjecture that this should be smaller. Not a good color. It should be smaller, right? Smaller than this. So that this one, and you can. So this is the result, and my point, my claim is that the key factor is that here you have a called SSH square. You have this component. Here you have right, because this is because of this. Okay, so the real question is this true? And one thing the answer is yes. One thing you may wonder is you can think of a random variable. If you think of the random variable with property W1, suppose you have a random variable and the property of the H equal to capital H is 1, right? By definition, because WH is NH divided by N. So straight term size, numerator is straight term size, and denominator is the total population size. So the summation should add up to 1. So if you have this random variable, if you think of this particular random variable, how do you write this one? Oops. Right? And then what is this? So but you already know the variance is this, right? So the variance is supposed to be greater than or equal to 0. So that means supposed to be square, right? So that basically is equivalent to this. So we basically so this one basically is equivalent. So we proved it. Okay.